Welcome back. We're here for some more networking fundamentals. Hopefully you've enjoyed what you've seen so far. It's not too much, too little, just right. Again, referencing Thomas's comments earlier about a hug of knowledge as we present more and more of this to you over the next couple of modules. We're going to dive right into our module 2. We're going to start talking about the OSI model today, and I'm going to hand it right off.
Okay, so module 2, defining networks with the OSI module. Again, let's talk about skill concepts for purposes of testing. The skills and concepts here are understanding OSI basics, defining the communications subnetwork, and defining the upper OSI layers, and defining the communications subnetwork. Standards. So we talked earlier about the English language. And because the English language has rules, that gives Christopher and I the ability, since we've grown up in different parts of the country, to still be able to communicate effectively. And maybe English speakers from other areas, we can still communicate effectively with those people. Standards allow devices, different manufacturers for hardware and software to be able to create hardware and software that intercommunicate. There are a set of rules that ensure this communication. Some examples of organizations that coordinate standards include the International Organization for Standards, the ISO. Now you may think, hey, International Organization for Standardization, ISO, well, that doesn't match up. Well, actually, since it's international, different countries have different names for this, so they've just standardized on the ISO format. And this is basically Federation of Standards from multiple nations, as I said. The American National Standards Institute, or ANSI, responsible for coordinating and publishing computer and information technology standards in the U.S., and then finally, the IEEE, International Electrical and Electronics Engineers, professional organization for the electrical and electronics field. People probably have heard of IEEE 802.3 or IEEE 802.
Just 802, really.
802.
There's a whole suite of standards within the 802 standard that we use all the time.
Correct.
Wireless, biggest one probably right now.
Wireless, wired, Ethernet, all from these IEEE standards. Yep. So these standards are things that we use every day and don't even think about it. And that's part of that's the good part, is the idea of a network is to be able to seamlessly access resources without you having to think about it. I can pick up my device, I can access my Facebook account, internet, web browse, my files in SkyDrive, Dropbox, whatever, and again, it's seamless. I, as a user, don't need to know anything, but as people wanting to become more familiar with networking will learn that these are the standards committees that help make that happen.
Yep, they're the ones that make it simple for everybody to talk to everybody.
Okay. So now let's talk about the OSI, Open Systems Interconnect. This is what makes network communication possible.
Essentially, yeah.
Is this model. The model's divided into 7 layers, and each layer provides services above and below it. So let's take a look at these layers. We're going to talk more about them later, so we're just going to give real brief overviews of them here. Layer 7, application layer, enables users and applications to access network services. People do get confused that they think that this is, as a user, a program that I use to access network services. It's not. It's the protocol the program I'm using uses to access network services. So just to clarify, layer 6, presentation layer, translates data into a common format. So we talked about ANSI. Another one is EBCDIC, and these are basically keyboard formats. Maybe different computers are using different formats. The presentation layer can translate that for you. The session layer, layer 5, establishes a communication session between devices. We've all been on the phone with somebody who, they pick up the phone, you have your conversation, you've initiated conversation with them, you've established connection, and then at the end of the conversation, they don't say goodbye. They don't end the session
cleanly.
seamlessly. Yeah, there's no clean. Yeah, they're just hanging on. There's dead air. You don't know what's going on. So they don't have a very good session layer protocol is the problem there. Layer 4, transport layer, manages message fragmentation and reassembly. Layer 3, network layer, this manages data routing and creating subnetworks. We've talked a little bit about subnetworks when we talked about LANs. Layer 2, data link layer, provides error-free transfer of data frames. And then finally, layer 1, physical layer, physical network media, and signal strengths. Now, this model may seem kind of daunting, but again, this is the model that enables network communication. And people are always like, how am I going to remember this model? So, Christopher, you had one that you use. Which one did you use?
So they're mnemonics. You can build mnemonics for this 7-layer system to remember what these are in order, hopefully, to remember. The one I had, there are a couple. The one that I've always known is all people seem to need data processing. Top down, all, application, people, presentation, seam, session, to, transport, need, network, data, data link, processing, physical. All people seem to need data processing.
Okay, can I give you mine now?
Absolutely.
Okay, so my one that I've always been fond of, starting layer 7 application layer, a priest saw 10 nuns doing push-ups. Politically correct? Probably not, but you're going to remember it, aren't you? There you go. You are welcome.
And just for fun, we also have one from the bottom up. If you want to start at layer 1, please do not throw sausage pizza away. Just in case you want.
Maybe it's about lunchtime. You're thinking about food. Please do not throw sausage pizza away. It works.
So the funny thing is, I've been in IT a long time. I know the 7 layers. I've known them the whole time. But I'm building this slide the other day, and I'm replacing, a graphic and turning it into an actual table so we can do more with it. And I actually use the mnemonic to write it out. So even though I know the layers, I'm like, application, all, process. I wanted to make sure that I had them all in the right order. So
right.
I refer to mnemonics I've been using for 15 years to.
Oh, they're really helpful.
Yeah.
I'm a huge fan of them. And those nuns doing push-ups, they're a fan too. So the OSI model layers, basically what we have here is, as we mentioned, it allows devices to intercommunicate. So what you see here is one device on the left-hand side under the title needs to intercommunicate with the other device. Maybe it's requesting a web service, a file and print service, maybe it's printing, whatever, there's communication. So the one starts, it goes through the different layers, and on the right-hand side of the table, it shows you what the data unit is called. Data, and then we get to segment, packet, frame, and then once we get to the physical layer, it becomes bits. It goes across the wire, that's our physical media, goes up the next one, and then basically it just gets deconstructed or reconstructed. So as the message goes down, it kind of gets deconstructed into the appropriate layer. As it hits the other side, it gets reconstructed.
Well, and the terms I use, I didn't want to go into too much detail as I was building these slides because we want to give people the right amount of information for this exam and to have the information they're going to need to do the job, but not necessarily so much information like, you know what, after 3 slides, I don't need to watch this anymore, I'm going home. The protocol data units on the right, you're not going to hear that term very often, but what happens as the data moves from top to bottom, you start with a piece of data at the application layer that is actually added to as you go from top to bottom. So it's either added to or in some cases broken apart. I start with a given amount of data, the next layer adds headers to that. The next layer breaks it into smaller consumable pieces to actually put on the wire and may add more information to those smaller pieces. So we're not going to dive into the actual technical details of what happens to each layer, but that's what this is describing, is that information is being, the data itself, your actual chunk of data is being modified, manipulated, broken apart, tagged, and built in a way that when it gets to the physical layer, those bits can be sent across and then successfully reassembled up the stack on the other side.
So now let's go ahead and start taking a look at the different layers. Layer 1, physical layer, defines the physical and electrical media for data transfer. Whether this is wired or wireless, they need standards of some kind. You need to know how to build the media. For wireless, what signal strength do I use? What signal channel do I use? For wired, what type of wires and cabling do I use? What type of jacks do I use? Physical layer components include cables, jacks, patch panels, punch blocks, hubs, and mouths. Physical layer concepts, and we've talked about some of this already, topologies. So what the network physically looks like. Analog versus digital encoding. When we think of analog, think of the old style analog clock. So it can be any of a time versus a digital. Digital clock is discrete. So it's either 10:05 and then it becomes 10:06. Maybe your digital clock doesn't have seconds on it. So let's take seconds away. So your clock is 10:05 and then it flips over and becomes 10:06. The gradation displayed to you is just it's one and then it's the next. For analog, so you have the analog, you have the hands on the clock, it can be any value within that system. So think of it that way, hands on a clock or digital media. Bit synchronization, baseband versus broadband, multiplexing and serial data transfer. We'll get into these topics more later. And the unit of measurements at this level is bits. So Ethernet standards. We've talked about the Ethernet. Ethernet standards is basically the standard for communication over networks. This has a frame type, so how data is packaged and sent over the wire. It has a physical media that can be described. As Christopher mentioned earlier, 802 is the Ethernet standard. Well, .3, .11 are the different standards of Ethernet that describe frame type, physical characteristics, electrical characteristics. All those are described in those standards. Defined physical and data link layers, so the first two layers. 100 base T is an example of an Ethernet standard. And to kind of break that down, the 100 stands for 100 megabit. The base is for baseband versus broadband. And T is for twisted pair cabling.
Which we'll look at later as well.
Yes. Baseband refers to the fact that the networks use digital signaling over a single frequency. Broadband systems use analog signaling over a range of frequencies, enabling multiple channels over the same physical medium. So again, if we think of digital and analog, not to hammer this, but I think this is kind of an important concept to understand. For digital, if you're looking at here, digital is discrete. So with digital, the data is so zeros and ones. It's here or it's here. So it's very discrete. For analog, it can be anywhere within this range. So anywhere within this range up here or down here can be analog. With an analog channel, devices can speak anywhere within this channel. For digital, you have these two areas. It can be here or it can be here. So again, something to think about, hands of a clock versus digital clocks. Layer 2, data link layer. So the data link layer establishes, maintains, and decides how transfer is accomplished over the physical layer. So basically now what we're talking about are frame types. How is that content encapsulated and put over the wire? Christopher earlier mentioned MAC addresses, media access control addresses. They're defined at the data link layer. These are hexadecimal addresses assigned to a physical network card or to uniquely identify these cards.
And in this case, MAC addresses ensure, in theory, although I don't think I've ever seen an example of this in the real world, they ensure uniqueness worldwide for network devices.
Correct. They actually, okay, so this is a little bit older. They had a problem where so for hexadecimal addresses, they assign different manufacturers different addressing schemes or different addressing assignments. For a while they had, and I don't even remember the names of the companies, they gave them the same assignments. So now they were putting out network cards that had the same MACs. I was at a training center, and again, this was a while ago when people had problems with network cards and you had to be really careful with static electricity. So in a training center, you're moving hardware. You're ripping open the case, you're removing network cards. So moving network cards, you use static would blow the address. So now you might have multiple systems that have the same MAC address, And the error that you would get is you'd bring one system online, it would be able to use the network. When you brought the other system online, it would blow the first system off the network. And then as you used each system on the network, it would blow the other system off the network. So
Sounds like fun.
Oh, it was really interesting to troubleshoot.
I imagine.
I would say it was good times, but it was not good times. It was the opposite of good times, actually. So network interface cards and bridges are examples of devices at this layer, and the unit of measurement at this layer is frames. So media access control, which we've talked a bit about already, ensures unique addresses for the different devices. We've talked about what happens if devices don't have unique addresses, and manufacturers are typically assigned ranges of addresses. They're 6 octets in length, written in hexadecimal.
And we're actually going to see an example here on the next slide.
So
it's animated, so not just by clicking.
Okay.
We'll get to an example in just a moment.
And props to Christopher. This is some of his graphic magic here. So know that all this graphic amazement is coming from Christopher.
Unless you hate it, in which case it was someone else entirely.
A vendor did it,
Yes.
I guess. Layer 2 switches are hardware-based and use the MAC addresses of each host computer network when deciding where to direct data frames. We've talked a little bit about switches already. So ports on the switch are mapped to different MAC addresses on the system. So if we look here, we'll see that, hey, these two ports are assigned to these two MAC addresses. So when a packet comes in for a specific device, it will only send to that specific device.
Yeah, and in this case, two things to note here. At the very top it says layer 2 switches. That is a valid term, although 99% of the time when you hear the word switch, it's a layer 2 switch. We probably won't get too complicated in this session or in this course and talk about layer 3 switches, which do exist. Little much to go into, considering it's actually overlapping with routers and switches. We're not going to go there. So usually when you hear the term switch, it's a layer 2 switch. And these addresses, they're not assigned per se to, say, the ports on this device, whereas a router is going to have IP addresses on the device. These, it just keeps track of. The switch knows what's plugged into it. It creates a little table, so it knows port 1 is that first MAC address. Port 6 is that second MAC address. It just knows that itself.
And so people aren't confused. People now will see devices that are switches and routers. So a lot of things that you'll see in the marketplace now, consumer-based devices, have multiple functionalities to them.
That's true, and a lot of it, it's a couple of different things. One, it's the combining of functionality. A traditional router would have a network card for a network and a network card for another network, and that's what would plug into it, and it would do the routing between the two. What you see now at home, especially if you're seeing a router, you know, you go to the store and you buy a router for your internet, that is a router in that it does route traffic from your network to, in this case, the internet. It's also a switch because they've provided you 4 ports to plug computers in your home or in your small office into. So it does both. It's not one device, essentially. It is 2 devices in that box. It's a switch and a router at the same time.
So VLANs, we've discussed VLANs a little bit already. Layer 2 switching can also allow for virtual networking or virtual LANs to be implemented. Again, this enables you to segment different areas of the switch, so entire bandwidth isn't thrown over either the switch, or you can allow communication of different segmented areas using the same switch.
Mm-hmm. Another fun little animation for this one.
Okay, so basically, like we just said, you can associate, hey, these 4 ports are one network, these 3 ports are another. Maybe you have accounting on one network, you have management on another. You do not want those to intercommunicate. You can use a virtual LAN to do so. Okay, so layer 3, network layer. This controls the operation of routing and switching to different networks. So it's using the network layer that subnetworks are created. This translates logical addresses or names to physical addresses. So as a user, I go to www.microsoft.com. The network layer is the one that translates that from that address or from that name to an address.
So when this happens, since we've already gone over the first two layers, we could talk about this now in a broader context. I want to go to www.microsoft.com. I do that. There's a process in the background that goes on that sends an IP back to my computer. It says that name has this address. And here we see Internet Protocol as the network layer protocol. There are services that will translate the name to the number. Like we just talked about in layer 2 with MAC addresses, there are also services that translate that IP into a MAC address. Or throughout my network, ways to figure out that that MAC address isn't on my network and I need to route it out somewhere else to find it. So this name translation or number translation happens at multiple layers. It's another one of those things I was talking about where the packets are being modified as they go up and down. Each of those layers has protocols and applications within it that are doing things to make sure those packets get where they need to go.
Devices that work at this layer are routers and IP switches. Network layer components include IP addresses and subnets, and the unit of measurement at this level is packets. So we talked about layer 2 switches. Layer 3 switches are basically switches that work at the network layer. So now instead of using the MAC address, we use the IP address. They have the same functionality, they just work at addressing at a different layer. Layer 4, the transport layer. So we've talked about the physical layer, the data link layer, the network layer. Now we're going to talk about the transport layer.
I'm sitting here listening, making sure he gets them all right. As we're going through,
Christopher's
he's throwing
testing
these out
me.
of my mind. We'll see how it goes.
This layer ensures messages are delivered error-free and in sequence with no losses or duplication. Protocols at this level perform segmentation, ensure correct reassembly, and perform message acknowledgement and message traffic control. So if I have a 10-page document, and with this 10-page document, let's go back to our postcard analogy. I have a 10-page document, and I can only fit 10 words on a postcard, and postcards are how I need to transmit information to Christopher. So as this goes down the stack, at a certain level, the transport layer, this 10-page document starts to get cut up into different smaller bite-sized pieces. These get put on postcards. When they hit the network level, it says, oh, and another thing that the transport level does is, so now I've cut all these up, I've put them on postcards, well, I number them. I say, hey, this is number 1, this is number 2, this is number 3. So when Christopher gets this information, he can reassemble in appropriate order.
And make sure I'm not missing any.
Exactly. So, do my postcards, network layer, I address them, I get to the data link, that's me walking to the post office box, opening the mailbox, and then the physical is me throwing it in, and then the mail carrier handing those off to Christopher. Christopher gets them all and receives them, gets them out of the mail. Now, what he needs to do is, so it went down my stack, and now back up Christopher's stack, he needs to reassemble and reattach all this stuff. And because I've numbered them, he can look at them and say, oh, I didn't get 15, you need to resend me 15. The unit of measurement used here is segments or messages. And this layer contains both connection-oriented or connection-less connections. So if we look here, connection-oriented communication, this requires both devices involved in the communication to establish an end-to-end communication. And I see Christopher smiling over here. I think he has something pretty exciting for us.
These are two of my favorite slides to have built. This was actually kind of fun for me.
So let's see what we have here. So at this point, okay, so the PC is basically, hey, I'm a PC, I'm going to need services. The server, hi, I'm a server, it makes an acknowledgement. I want to send you something important. Okay, I will watch for it. So we have this back and forth communication that's a connection-oriented communication.
We're aware that something's going to happen. We're making sure it happens correctly and properly and in order and in time.
And again, as we mentioned, packets not received can be resent.
Yep.
So now let's look at connectionless. So connectionless, end-to-end connection is not necessary before data is sent. So connection-oriented, maybe I'm looking at a file transfer. Maybe I'm looking at a web page. Connectionless would be streaming a video. I don't necessarily need every frame, but I do need certain information. So that information is kind of sent. We go back to our radio analogy where somebody's just talking. They don't know if the message is getting received or not. They're just sending the information out. That's kind of a connectionless communication. Every packet is sent, still has a destination in the header, but we don't necessarily know if it's going to be received. So here the server, I have communication for you, listen to me. And here the client's kind of sleeping because there's no response.
They're just listening. Server sending it out. Hopefully someone's listening.
Yep. So connection-based protocols. The transport layer contains both connection-oriented and connectionless. We have TCP, Transmission Control Protocol, that provides a connection-based system, and UDP, which provides a connectionless, unreliable transport system. TCP and UDP, so TCP transport's used for logging in, file and print sharing, replication. So basically, when you need acknowledgement, you use TCP IP. UDP is used for one-to-many communications, broadcast, multicast, IP datagrams, audio streaming, things of that nature that don't need to be acknowledged.
Yep. Hopefully someone's listening, and if things get dropped in transit. This is actually a protocol used in situations where packets can't be resent. One of the best examples I have of that is VoIP, voice over IP. If I have a phone that's working on an IP network and I'm having a conversation with somebody anywhere else, if the packet that I'm creating by talking into my device that's getting assembled and run through the layers and sent across the wire, if that packet doesn't make it, I can't re-have that millisecond of the conversation. It's just gone. So
otherwise you get chop, jitter,
yep, which you'll hear. You'll hear gaps, and that's because there are packets that may not make it for any one of 1,000 reasons, and if they don't, there's nothing you can do about it.
Well, and there are certain things that, say a conversation. If, as Christopher and I are having a conversation, I have to acknowledge every word he says, that's really going to delay the conversation. Versus we go to a more connectionless system where he can speak long sentences and then I can respond in long sentences. That's more of a connectionless system where he's hoping I'm getting most of his words and I hang on 85% of them. And he probably hangs on 75% of mine. I'm not sure, but so
we'll go with that. Is how much of it I'm remembering.
So keep in mind there's certain overhead to a connection-oriented system.
Yeah.
So ports. Ports are a layer 4 protocol that a computer uses for data transmission. They're logical communication endpoints for specific program on computers for delivery of data sent. For example, we have two computers communicating. One computer is requesting web services from another. If I just send to the IP address a request for web services generically, it's not going to know how to respond to that. So what I need to do is specifically give it a port. I don't do that. The protocols do that. Give it a specific port to say, not only is it this address, it's this specific program I'm talking to. So go back to mail, our postcard analogy. Let's say Christopher and I have multiple postcard conversations going on. So I might address this postcard conversation as port 80, which is our term paper. Another postcard conversation we have might be port 443, which refers to some other conversation we have. So basically, ports allow you to not only say this specific device, but this specific application or process within this device.
Is what I'm looking for. The analogy I used to use was a house. I'm sitting home on my couch, my doorbell rings. Now the analogy at this point is IP addresses. someone out there in the world has found my IP address. That IP address is how they're going to find my house. They use a street, a city, a state, a zip code to narrow it down. And an IP address is just that. They've narrowed it down to my house. They come to my house, they knock on the door. All I know is someone's at the door. I have to walk over the door, and I have to look through a peephole or out a window to find out what they want. That's what those ports are, is what they want. If it's a guy in a little brown outfit with shorts on, holding the box in his hand, I know he wants to deliver me a package. I'm going to open the door, I'm going to take the package, I'm going to sign for it. If it's a guy also possibly with shorts on, but in blue outfits and maybe wearing a hat, he's probably got some mail for me that I'm going to want to open up and read, and I might actually have to go get some mail and bring it to him to take with him when he leaves. So the ports act as almost the uniform. What are you here for? What do you need when you get here? And as another part of this analogy for fun, we talked about firewalls earlier, which are sort of secure routers. That's what the peephole on your door is, so you can look through and see.
Oh, that's very nice.
That guy's wearing a little brown outfit with shorts. I probably want to open that and take that package from him. That guy's got a knife in his hand. We're going to go ahead and keep the door shut. We're not going to open the door for that one.
Well, I mean, you might. What if you want to live dangerously? Or what if that's the knife that you ordered from the...
Yeah, but the fact he's holding it in his hand might be a little suspicious.
Yeah, might be a little worrisome.
I would think that would come in a box, but I guess maybe if that's how you deliver things.
Okay, so that basically outlines ports. And then in this next section, we have the generic ports. Well, not generic. These are very specific ports. So these port numbers are always associated to these protocols. 21 FTP. So when you get on a site and try an FTP, you're using port 21. Port 23, Telnet. I mentioned port 80 before, HTTP. So any web browsing you do is using port 80. If you want to do secure browsing, 443, HTTPS. And then you can kind of look through this list and see the different ports that are associated with the different programs.
So the way to impress your friends, if you are that kind of geek, you have contests at your house. Who can remember the most port numbers and what services are assigned? People will flock to your parties if you start them off with port competitions.
How could you become more popular than that?
You can think of a couple of ways.
Okay, so layer 5, session layer. Session layer manages session establishment, maintenance, and termination between network devices. Example, when you log on or log off, again, we go back to that phone call analogy. When you start up on a phone conversation, hello, how are you? You initiate the conversation. I've called about blah. Hey, Christopher, I've called about this presentation. So Christopher would answer, we'd go back and forth, and then when we were finally finished, you'd be like, okay, goodbye. And then if he had a decent session layer protocol, he would say goodbye also, and we would cleanly disconnect the session. This layer also controls the name and address databases for OS, such as NetBIOS. NetBIOS, Network Basic Input-Output System, is a protocol that works at this layer for naming, creating names and associating names to computers. And actually, Microsoft was one of the people or one of the companies that implemented this for a way to associate names to computers.
Yep, a long time ago. This was one of the protocols Microsoft implemented. It's not so widely used anymore, but it's still out there. You'll still see it.
Layer 6, the presentation layer, translates data format from sender to receiver in various OSs that might be used. Concepts include character code conversion. Remember I mentioned maybe ANSI versus EBCDIC, the different keyboard types. Or not necessarily keyboard types, but data representation. How do you represent an A in this system versus how do you represent an A in this system? Presentation layer is the one that translates that. Redirectors work at this layer, such as map network drives that enable a computer to access file shares on a remote computer. Again, a translation system. And then finally, layer 7, application layer, serves as the window for users and application processes to access network services. End user protocols, FTP, SMTP, Telnet, and RAS work at this layer. Again, this isn't supposed to be confused with the application that you're working with. This isn't mail. This isn't the mail UI that I'm using. The mail UI that I'm using that sends information down the stack, it hooks into the application layer. The program itself isn't the application layer. And then again, the OSI model revisited. If we take a look at the slide here, we see application, presentation, session, transport, network, data link, and physical. We see the different protocols associated with each layer, and then different devices that might be associated. One thing to keep in mind, or that I always thought was kind of interesting, is notice TCP and IP are at different levels. People think that TCP and IP are opposite of the same thing. They're actually not. It refers to a portion of the transport protocol and a portion of the network protocol. In the scheme of things, not overly important, but a fun geek fact.
Again, ways to impress your friends at parties.
Exactly.
We're chock full of ways to impress your geek friends at parties.
Obviously, Christopher and I don't go to a lot of parties,
We do not.
but if we did, we would have knowledge to share with you and would be happy to do so. The TCP model. So we've talked about the OSI model. The TCP model is actually a little bit different. It's similar to the OSI model, and it allows interconnectivity between devices and allows intercommunication. The TCP model is only comprised of 4 layers. The application layer, which defines the TCP IP application protocols. The transport layer that provides communication session management. Internet layer, packages and routes data. And then the network interface details how data is physically sent through the network. Something interesting about the TCP model is that the TCP model doesn't really designate on the OSI level a physical or data link layer protocol. They only give information for the upper layers and then figure, hey, data link and physical, we're not going to worry about it. We're not going to worry about those layers. Other companies or other areas can worry about that. We're just going to worry about the upper level transport. Let's take a look at the OSI model compared to the TCP model. Again, you see here the OSI model, 7 layers, the TCP 4 model, 4 layers. The application and TCP model is equivalent to the application, presentation, and session layer in the OSI model. Transport layers are equivalent. Network layer routing in OSI model is similar to the internet layer routing in the TCP model. And then again, the network access layer in the TCP model isn't really concerned. They're like, oh, okay, well, you can use Ethernet, you can use FDDI, you can use whatever you want. We don't care. We're more concerned with the upper levels. And most of you probably already know this, but if you don't, TCP/IP is the protocol used for internet standards and is the protocol used for internet communication. Wow, we're at the summary already. Who would have thought that we'd got through all this information already?
Time flies when you're having fun.
It flies sometimes when you're not having fun, but hopefully everybody's having a good time.
I wish you did that more often. Yeah, they better be.
So basically the summary here, understand the OSI model by defining each of the layers from a theory perspective. 7 layers: application, presentation, session, transport, network, data link, and physical.
Nice. Well done.
I see Christopher over here like ticking them off as I go down. Priest saw 10 nuns doing push-ups, was kind of going through in my head. You need to be able to separate the functions of the lower levels of the OSI model from the upper levels where message creation begins. Basically what they're talking about here is understand the physical areas of the OSI model compared, the physical and routing levels compared to basically packet assembly, fragmentation, reassembly, session, connection-oriented, connectionless. Those are kind of different areas. Understand the differences between layer 2 and layer 3 switches. Layer 2, MAC address, layer 3, networking or IP addresses. And differentiate between the OSI model, 7 layers, and the TCP model, 4 layers.
I feel like we need a burrito mnemonic somewhere.
A burrito?
Every time I hear 7 layers. Every time I hear 7 layers.
You're thinking burrito?
I'm thinking burrito, yeah.
And we just had lunch, too.
I know. That might be why. That could be why.
You're thinking food.
I guess so.
Finally, additional resources and next steps. Christopher, what do we have?
So we saw this one in some of our other modules. It's the same information. The MTA Networking Fundamentals Microsoft Official Academic Course book. Our instructor-led courses, there are 4 of them, 2 specifically that pertain to networking fundamentals. One of those is a 5-day 2-pack to save you some money and some time, networking and security combined. And then exams and certifications. The reason we're here is to hopefully get you started on preparing and able to pass the 98-366 Networking Fundamentals Microsoft Technology Associate exam. Those exams never get any shorter, that's for sure. Those titles they just get longer.
Believe it or not, sadly, we're at the end of this module. So we've talked about the OSI model, we've talked about standards committees, we've talked about TCP, we've talked about burritos. Have I missed anything that we discussed?
I don't think so. Once we got burritos, we were good. Module closed.
Yeah, I think we're pretty much done with what we need to say here. Thanks for listening, and watch the other videos. Why not?
Yeah.